Good morning to everybody. Welcome to session 2. In this session 2, let me discuss the electrical model of a transmission line. In this particular session, we will discuss electrical model diagram, definition of primary constants, and you know what you mean by the definitions of secondary constants. Before going for this session number 2, let me recap what we did in the session number 1. So in the previous session, we did the transmission lines, that is definition of transmission line we went through, and we went through the types of transmission lines based on the power and frequency, and we went with the applications of transmission lines. So let me recap what you mean by transmission line. As you know, as I already told, transmission lines are intended for carrying the radio frequency energy or RF energy from one place to desirable place or source to destination. For a practical example, the TV and antenna should be there with each other, but it's not practically possible. Antenna will be located outside your home, TV will be inside. To carry the signals from TV to antenna, I need a transmission line. This is one of the simplest example that I can quote for you. Based on the power and frequency, I divided into broadly two types. First one is power line, which carry an huge power but with what fixed frequency. For in the case of India, 50 Hertz. In US, it will be around 60 Hertz. Based on next one is communication lines. This is the type of transmission lines we discussed. What do you mean by communication line? Communication lines are intended for carrying the variable range of frequency but with a minimum power. And we went with the many types of communication lines are available, but we broadly went to with some four types like coaxial cable, parallel wire, and waveguide. As you know, waveguides are intended for micro frequency or electromagnetic radiations. That works on the principle of optical fiber communication or total internal reflection. In the same fashion, we are going to learn in this session too what will be the electrical model diagram of a transmission line. That means how you analyze electrically one transmission line, that we are going to deal today. And what are the primary constants and what are the secondary constants. So before starting this one, so what do you mean by primary constant? What do you mean by secondary constants? These are the constants. They are going to describe the characteristic of a transmission line. If you want to purchase one transmission line in a shop, these are the things you should quote to that particular shop owner, that I want this primary constant and I want this secondary constants. Or in the case, in general, if I discuss, if you want to purchase one moped or some scooter or some motorcycle, so what are the constants, what are the features that you are going to looking for? There will be thousands of factors. Basically mileage, speed, petrol, then the what maintenance. These are the thing I can say primary or secondary constants. So in the same fashion in transmission lines also there are separate characteristics which determine the capability of transmission lines. Let me explain in the upcoming class now. So what are the learning objectives after completion of these sessions? You are going to understand the meaning of electrical model of transmission line, and you're going to get the brief knowledge about primary constants as well as secondary constants. So what is the session outcomes? Student will be able to understand transmission line that can be modeled into electrical parameters. Student should understand the meaning of primary constants and secondary constants of a transmission line. So in the diagram you are seeing the electrical model of a transmission line. Whenever you are getting a word electrical, there includes resistance, inductance, capacitance, conductance and so more. But here, how I have modeled the electrical model of a transmission line. If you see here, this inductance or resistance and inductances are connected in series. Here, capacitance and conductances are connected in shunt or parallel. So this is for one unit length. For this is for if I take a cable or electrical line from Hirur to Bombay. So this is Hirur to Bombay. I'm having some 800 to 900 or 1000 kilometer I'm having. So these are the parameters will be there for every kilometer. You can choose for every 100 meter. You can choose for every meter even. That means your electrical transmission line is a distributed parameter. That means this RLGC will be distributed throughout from Hirur to Mumbai. If I take the line, for example, from Hirur to Mumbai, these RLGC will be distributed. Here also it will be distributed. If I take this is 1 kilometer, this is another kilometer RLGC. So it will be distributed throughout the line. That means electrical transmission or transmission line is a purely distributed parameter in terms of resistance, capacitance, conductance, and capacitance. In this manner, I can conclude transmission line can be parametered or modeled in terms of R, L, G, and C. Let me explain once again. In general, if I take an example from Hiriyur to Mumbai, I am laying a transmission line. The thing is, each kilometer or each length of a cable will be having R, L, G, C. You can model that RLGC per every kilometer or per every meter even. So in the same fashion, so this RLGC will be distributed throughout the line from source to destination or from starting point of the transmission line to ending point of the transmission line. In the diagram, you can see since R and L are connected in series, I can get series impedance Z in terms of R and L. I repeat once again, since resistance and inductance, this is R and L. Since resistance and inductances are connected in series, I can get the total series impedance in terms of Z is equal to R plus J omega L, where R is an resistance per kilometer, L is an inductance per kilometer. So here I'm having a complex number J and omega. Omega is an 2 pi f. In the same fashion, we know this C and G, capacitance and conductances are connected in shunt or parallel. Hence, I can get admittance in the terms of Y is equal to shunt admittance is equal to G plus J omega C, where G is in conductance and C is in capacitance. J omega is an what complex quantity, where omega is an 2 pi f. I recap once again, electrical model can be expressed in terms of electrical parameter. The number one point is that whole electrical parameters will be distributed throughout the line in terms of R, L connected in series and GC will be connected in parallel or shunt. As I summarized here, transmission line is a distributed network. It's not a lumped, it's a distributed network. It is a cascade connection of infinite sections. I told you before, the cable may be 100 kilometer, but you can cascade to infinite divisions, where each division can have R, L, G, and C. In terms of RL, I can get series impedance Z. In terms of GC, I can get shunt conductance Y. Each section consists of series resistance, inductance, shunt conductance, and capacitance. What do you mean by primary constants? That means which are the very important futuristic points regarding to transmission lines. Transmission line has the following primary constants as I told. R, it is defined as loop resistance per unit measured in ohm per kilometer. That means the unit of resistance is ohm. I told the resistance is per unit length. If you multiply by the kilometer, you are going to get the resistance for that particular length. Second one is L, defined as loop inductance per unit length measured in, I told inductance will be measured in Henry per kilometer. If you want for total wire, you need to multiply that by the total distance of a wire. You're going to get kilometer get cancels. You're going to get only Henry. That means total inductance. In the same fashion, C is defined as shunt capacitance between the two wires per unit length, that is expressed in farads per kilometer. If you want the capacitance for total length of the wire, you need to multiply by the length of that particular wire, so that farads per kilometer multiply by kilometer, I am going to get the farads. That means the total capacitance of the particular line. In the same fashion, I'm having G. This is defined as conductance per unit length. There are mho per kilometer. Mho is an unit for conductance. If you want for total length, what is the conductance? You need to multiply by the length of the wire, so that you will get kilometer get cancels. You are going to get only mho. That means the primary constants of a transmission lines can be defined as R or loop resistance, L or loop inductance, C or shunt capacitance, G or conductance per unit length. Here I can summarize that R and L are connected in series. Primary constants are further related to series impedance Z and shunt admittance Y given by Z is equal to R plus J omega L, where ZD is nothing but series impedance. R is total resistance of the cable or total resistance of the transmission line. J omega is equal to 2 pi f, and L is an inductance of a particular transmission line. In the same fashion, I can conclude this G and C in terms of Y or shunt admittance. Shunt admittance is given by G plus J omega C, where G is in conductance, J is in complex quantity or root of -1, omega is equal to 2 pi f, and C is equal to capacitance in farads. You should have it in mind because in the further derivations, I'm going to quote only Z and Y. Z is nothing but series impedance and Y is nothing but shunt admittance. Please have it in mind, my dear students. Now I went with secondary constants. Previous slide I gone through the primary constants, namely R, L, G, C, which are distributed throughout the transmission line. In this particular slide, I'm going through the secondary constants. The secondary constant, there are two things. Two things are there. One is characteristic impedance denoted by Z0 and propagation constant denoted by gamma are called secondary constants. I repeat once again. Characteristic impedance denoted by Z0 and propagation constant denoted by gamma are called as secondary constants. Now, if a line is terminated with its characteristic impedance, then line behaves as an infinite line, hence no reflections. Here, the point to you to understand is, I told the line is for defined length. If you don't want the reflections comes in the upper coming classes. So, if the characteristic impedance of a line is equal to the line impedance, that means I told the line will be having source and destination. If you take the destination impedance or if you take the load impedance, if that particular load impedance is equal to the characteristic impedance of a line, that means ZL is equal to Z0. At that time, there will not be any reflection because the line behaves as an infinite line. That means no end at all. And there will not be any reflection. So my dear students, when you get reflection, if you hit the ball to wall, then only you get the reflection from the ball. If you throw the ball, if there is an infinite space, then how can you get the reflection? It's not possible. In my transmission line also, I want the line must be infinite. How it happens? It happens only when the characteristic impedance of the line is equal to the load impedance of the line. My line behaves as an infinite line. Infinite line is desirable for me. Why? Because there will not be any reflections. I told the example of one tennis ball. If you throw towards the wall, if there is a wall, there will be reflection. According to Newton's third law, for every action, there will be equal and opposite reaction. If there is no wall, if I throw the ball will not be reflected towards you. I don't want any reflection in my transmission lines. Please have it in mind. I don't want any reflections in my transmission lines. So what I need my line should be infinite. To make my line infinite, what I need, the characteristic impedance of a line Z0 must be is equal to the load impedance of a line. This is the desirable characteristic of a transmission line. I told for lossless lines. Lossless means what? If there is no reflection. So I told, so what do you mean by characteristic impedance? I told secondary constants are two. One is characteristic impedance and another one is propagation constant. Characteristic impedance is nothing but square root of Z by Y. I told Z and Y are very important. What do you mean by Z here? Z is a series impedance divided by shunt admittance. I can once again simplify this one. Square root of Z is nothing but R plus J omega L divided by G plus J omega C. In lossless lines, R will be is equal to G. That means in infinite line, I can have resistance will be is equal to conductance. Hence, further simplification, I get Z0 or characteristic impedance is equal to root of L by C. What do you mean by L? L is an inductance per unit length of line and C is an capacitance per unit length of line and Z0 is an characteristic impedance of the line. Let me go with one more secondary constant, that is propagation constant. It represents in which manner the propagation takes place along the transmission line. In the propagation, definitely we'll be having two things. One is attenuation might be happening. Another one is there might be a chances of phase shifting from transmitter to receiver. Anyway, so the propagation constant gamma is given by square root of z into y, where I told z is an series impedance and y is an shunt admittance. Further simplification, I get gamma is equal to root of zy is equal to root of z is equal to r plus j omega l into g plus root of g plus j omega c. It can be correlated with alpha plus j beta. That means if you relate with real components, you are going to get alpha. If you relate with the imaginary components, you are going to get beta. So why I am doing this one? So the real components are going to give alpha, that is nothing but attenuation constant. Whenever you are doing the propagations, there is a chance of attenuation of the messages. So hence, the secondary constant, propagation constant, will be related in terms of two things. One is alpha and another one is beta. Alpha is a purely real component. It is nothing but attenuation constant. It is given in terms of Napier per kilometer. Napier is it's a unit of attenuation. Second one is beta. If you relate the imaginary components, you are going to get beta or nothing but phase shift component. Anyway, you know the phase shift will be taken in terms of degrees or radians. Here, beta will be given in terms of radians per kilometer. I repeat once again, there are two types of secondary constants. I show once again. One is a characteristic impedance, another one is a propagation constant. Characteristic impedance is nothing but Z naught is equal to root of ZY, where Z is a series impedance divided by shunt admittance. In the same fashion, I went for the one more secondary constant called by propagation constant or gamma. It represents the manner in which the propagation takes place along the transmission line. Gamma can be given by root of z into y, where z is a series impedance. If I further simplify, I get root of r plus j omega l into root of g plus j omega c. And if I relate the real components, I get alpha or attenuation constant in terms of Napier per kilometer. And if I relate the imaginary components, I get beta or phase shift components in terms of radians per kilometer. Or gamma can be given in terms of attenuation constant plus phase shift constant. So in this particular session, what we discussed the electrical model of a transmission line. I told the electrical model of a transmission line is nothing but it's purely distributed. It is not lumped. If the line is having thousands of kilometers, each per kilometer or each per meter will be having RLGC, or each per unit length will be distributed in terms of primary constant and secondary constants. Primary constants are nothing but RLGC. Secondary constants are nothing but Z naught and constant, that is propagation constants. And we discussed the associated primary and secondary constant, what we discussed in the previous slides. So let me have some multiple choice questions based on the previous slides what we learned today. So question number 1: in electrical model of a transmission line, resistance and inductances are connected in 1 parallel, 2 series, 3 both 1 and 2, 4 none of the above. The answer is series. Since I told you in the brief explanation of that block diagram of electrical model of a transmission line, the first two components, resistance and inductances, are connected in series. Now I see what is the second question. Hence the answer is 2 series. Question number 2. In electrical model of a transmission line, conductance and capacitance are connected in option number 1 parallel, option number 2 series, option number 3 both 1 and 2, option number 4 none of the above. The answer is option number 1 parallel. I told in the electrical model of a transmission line, R and L will be connected in series, whereas C and G will be connected in parallel or in shunt. Hence, the answer is in electrical model of a transmission line, conductance and capacitance are connected in parallel. I go for question number 3. In a situation where load impedance equals the characteristic impedance, it means in a situation when your load impedance is exactly equal to your characteristic impedance of the line, what will be the happen? What will be the situation? Option number 1, high reflection. Option 2, no reflection. Option 3, infinite line. Option 4, both 2 and 3. The answer is option number 4, both 2 and 3. I told no reflection or infinite line. In case if you want to get no reflection on a line, the line must be infinite. That means no reflection and infinite line are one and the other. When this happens, ಯಾವಾಗಾಗುತ್ತೆ ಇದು? When this happens, it happens only when the load impedance of a line is exactly equal to characteristic impedance of a transmission line. At that case, the line behaves as an infinite line. If the line is infinite, there will not be any reflection at all. Hence, the answer is option number 4, both 2 and 3. Question number 4. At very high frequencies, transmission lines are used as option 1, tuned circuit, 2, insulators, 3, antennas, 4, resistors. The answer is tuned circuits. At very high frequencies, we can use transmission line for tuning purpose. In AM or FM, some fine tuning can be taken place with the help of transmission lines that you are going to learn in the upcoming sessions. Question number 5. Hence, the answer is option number 1, tuned circuits, or at very high frequencies, transmission lines can be used as an tuned circuits. Question number 5. The distribution constant of the transmission line is option 1, resistance, option 2, inductance, option 3, capacitance, option 4, resistance, inductance, capacitance, and conductance. The answer is resistance, inductance, capacitance, and conductance. Why? Because I told the transmission line itself is a distributed parameter. It is distributed in terms of primary constants and secondary constants. What are the primary constants? Resistance, inductance, capacitance, and conductance. And the answer is option number 4. Question number 6. Transmission line can be treated as high pass filter, low pass filter, band pass filter, and band reject filter. The answer is option number 2, low pass filter. If you learn the properties of low pass filter, you can get to know, since the construction of a electrical model of a transmission line is such that R and L are at the source side and G and C are at the destination side. So hence, it can be treated as low pass filter. That means it can pass the frequency up to FHR or something. Lower frequencies can be passed in the transmission lines. Hence, the transmission line can be treated as low pass filter. Question number 7. For a lossless transmission line, characteristic impedance is given by option number 1, LC, option number 2, root of L into C, option number 3, root of L by C, option number 4, none of the above. The answer is option number 3, root of L by C. For a lossless line is, once again, you think it is nothing but R is equal to G, or it's an infinite line, or is nothing but it doesn't have any reflection. In that particular line, what is the condition? The condition is nothing but the answer is root of L by C. Question number 8. A lossless line has Z0, which is Z0 is nothing but what? Characteristic impedance. Characteristic impedance should be what? In what case? In a lossless line. I repeat the question. Question number 8. A lossless line has Z0 or characteristic impedance, which is option number 1, inductive, option number 2, capacitive, option number 3, complex, option number 4, resistive. The answer is option number 4, resistive. For a lossless line, the characteristic impedance must be always resistive. It should not have any complex or active components. It must be resistive. Question number 9. Transmission line will be distortionless if option 1, LG is equal to CR, option 2, LC is equal to GR, option 3, LR is equal to GC, option 4, LG is equal to 1 by CR. You should have it in mind. L means inductance, G means conductance, C means capacitance, R means resistance. And the question is distortionless. That means there should not be any distortion, or there should not be any reflection, or there should not be any losses in the line. In which case it happens? The answer is option number 1. Lg is equal to Cr. This is the condition when my line behaves as an distortionless. So for a transmission line to be distortionless, I need a condition Lg is equal to Cr. Hence the option is number 1. Question number 10. A finite transmission line behaves as an infinite transmission line when the load end is question number option 1 short circuited, option 2 open circuited, option 3 terminated by any impedance, option 4 terminated by characteristic impedance of the line. Understand the question? A finite transmission line, that means it is having a fixed length. It behaves as an infinite line, that means that there is no end at all. When it behaves, a finite length behaves as an infinite line. When? The answer is option number 4, terminated by the characteristic impedance of the line. I repeated multiple number of times. Whenever the load impedance is exactly equal to the characteristic impedance of the line will not be having any reflections. Why there will not be any reflections? Because the line itself behaves as an infinite line. There will not be any boundary or end so that your incident energy will be reflected back. Hence the condition is for a finite transmission line to be behaves as an infinite transmission line, the condition should be the load end should be exactly terminated or equal to the characteristic impedance of the line. Finally, thank you. Thank you. Stay home, stay safe.